So I'm sure some of you here this evening might not be from Manitoba, but you've probably had a chance to experience some of the frigid cold that essentially ruins so many perfectly good days. But not only do these temperatures make us uncomfortable, make us wonder why exactly we still live here, but they also disrupt many physiological processes in our body, such as the delivery of oxygen to our tissues. As oxygen is absolutely essential to all mammalian life, a primary component of your blood is an oxygen-carrying protein called hemoglobin, pictured center. Hemoglobin picks up oxygen at your lungs and then delivers it throughout your body. But the problem with hemoglobin is that it really doesn't like to be cold, and it doesn't work very well when it's cold. So as temperature decreases, hemoglobin tends to hold onto that oxygen a little too tightly, and it won't deliver that oxygen to the tissues that need it. So as a result, these cold, hypoxic tissues, much like your fingers as you're scraping ice off your car, well, they eventually turn blue and they die. So to compensate, we put on warm clothing, we come inside a lecture theater, or we leave Winnipeg entirely. But something like a woolly mammoth, it spent most of its days standing barefoot in the cold, so it didn't have the luxury of wearing boots. How exactly did its hemoglobin get oxygen to these cold tissues? Had it evolved a hemoglobin that was able to maintain function even though its blood literally ran cold? Well, to trace the evolution of hemoglobin function, we need to look at a model group of organisms, a group whose evolutionary history is well understood, a group who originated in a warm climate and had a few members move to the Arctic. Then we can map the change in hemoglobin function that arises with Arctic colonization. So this model group is the Afrotherians, who originated in Africa. And then the woolly mammoth up above and stellar sea cow down below, they moved to the Arctic. So their hemoglobin might hold the key to understanding oxygen delivery at low temperatures. There's just one tiny problem: they're both extinct, and hemoglobin doesn't fossilize. But fortunately, I've found a way to work around that. I've developed a method that allows me to sequence a large number of specific genes from ancient remains. I can then use these gene sequences to genetically modify bacteria and have bacteria reproduce a hemoglobin protein that exactly matches theirs. Functional tests on these resurrected hemoglobins can then allow me to elucidate the mechanisms of oxygen delivery at low temperatures. So we can then use the information garnered from these hemoglobins in the development of blood substitutes that are specifically used for hypothermia-dependent surgeries, whereby the entire body is cooled right down in order to stop the heart and perform surgery on it. So I envision that one day, somebody undergoing open heart surgery will have oxygen being delivered to their cooled tissues by something similar to the hemoglobin protein that ran through the blood vessels of these iconic lineages tens of thousands of years ago in the Pleistocene ice ages. Thank you.